Hi, so the chapter is about the kinetics, chapter 12. What we need to understand here is that there's a lot more about the solution chemistry, um, chemical reaction rates. We are interested in the speed of reaction and how we can do that, how the stoichiometry can play its role, how we can calculate the average and instantaneous rates. We'll learn how to calculate how to find out the rate law for a particular chemical reaction, and because rate constants talk about the speed of the chemical reaction, we have to look for the rate constant and how much the reaction order plays its role. So there's a method to do that that we call the initial rates method. We learned that in this chapter. We'll also so we are looking at how the concentration of the reactants affect the rate, speed of the reaction. Also, we're going to be looking at how the temperature affects the rate of the reaction. And there it comes to the half-life and see how we can calculate the half-life means half of the reactants to be done at what time. Whatever the time is where the half of the reactants are done is this is what we call half-life. We'll also learn collision model, Arrhenius equation, activation energy, the energy that is required for the reactants to be converting into the products, and how we can expedite the reaction with the help of catalyst. Catalyst reduces the amount of activation energy required for that. And it's a breakthrough, actually, the catalyst that we always talk about in chemistry. So talking about a lot more chemical kinetics, we talk about the concentration of reactant, concentration of catalyst. We talk about temperature, that's the profound effect on the rate of reaction. We also talk about the surface area of the solid reactants or the catalyst because that comes in contact. Collision, efficient collision, effective collision for a chemical reaction is important. So going in proper orientation, or so the collisions are happening, but if these collisions are not in proper orientation, the chemical reaction is not going to proceed. So that's one of the factors that we always talk about. So when we are doing the chemical reaction rates, and the iodine clock 1 and iodine clock 2 experiments actually are the experiments for the reaction, to understand the rate of reactions. In iodine clock experiment, what you will exactly do in the lab, you will follow a rate of reaction. You will follow the progress of a chemical reaction, and then you will record time. That's how we're going to be doing it. And then you probably will control the concentration of your reactant and will see how it affects. And then you can also bring the time in, that how long it takes, how short it takes if you change the temperature for the reaction to proceed. And because the temperature changes, the rate constant. Um, so what you need to understand is that you need to have, because you're not looking at the reaction directly, so you need to have some system or some assays or some protocols to find out what's going on in the chemical reaction. And that's usually a phenotype that you are interested in. So if you look at the if you pay attention to the left hand side to the right hand side in this um, reaction thing going on here, you see it was colorless, and after 15 seconds turned into yellow, and then orange, and then all the way to the brownish stuff. And that's where we see the progress, and we see this color, and we can actually get this color recorded in terms of measurement through the colorimetry. So we bring experimentation and we call it colorimetry, and we can record how much color change corresponds to the depletion of the reactants in the chemical reaction. We can do that definitely. So what is going on in the chemical reaction, that the reactants are depleting, because the reactants are being used and products are being formed. So the rate of reaction, when we talk about the rate of reaction of reactants, is going down as the time progresses, while the rate of formation of product goes up. So they go side by side though. So what we can do here, we can write down the rate expressions, and these are just the mathematical representation of rate of reaction. How do we write it? We have to look at a balanced chemical reaction for that. So there are different terminologies in this chapter where we are talking about rate expressions, and then we're going to talk about rate laws. So these are two different things: rate laws versus rate expressions. Right now we are talking about rate expressions. we can use the balanced chemical equation for and for any substance in that particular reaction, either product or reactant, we can write down the rate expression. What is rate expression? Is that if the time changes from one point to another time, how the concentration is changing. That will have, because it's going to be the concentration over time, the change in concentration over the change in time that you use to calculate the rate. So if you are able to look at that, and you can always say, why does this make sense? Because we have to take the stoichiometry of the chemical reaction into account, because in that ratio, things are being depleted and things are being formed. So if you talk about the rate of dinitrogen pentoxide, then because it's a reactant, so we always use negative sign for that. And then we say the change in the concentration of which ratio. The mole ratio is 1/2. That's how it's changing. Change in the concentration of N2O5 over the change in time, whatever the time period is. So for the reactants, we have to show the negative sign because they're depleting, going down. For the products, we have to show it as a positive number. So it's going to be 1/4 over change in the concentration of NO2, which is nitrogen dioxide, over the change in time. So that's the same thing that you're going to be doing for oxygen. It's 1:1. So you're just going to be, see the difference is only is that this negative here, this is positive here, because the reactants are depleting and the products are being formed. So if we are learning how to write the expression, the rate, the reaction rate for the reaction rate, then you're just going to do it for all of them one by one. How the rates in terms of these species relate, how are these rates are related to BR2. When you write it down, you're just going to say 1 minus 1/5 change in the concentration of BR negative over change in time is equals to, again, is going to be negative change in the concentration of BrO3 over the change in time is equals to, then again, there is going to be a negative for hydrogen ions. It's going to be 1/6 change in the concentration of H pluses over the change in time, right? And for all the products that you see here, you're just going to write down plus, plus, plus 1/3 change in the concentration of Br2, and it's going to go to the change in time, and that's going to be equal to 1/3 change in the concentration of water over the change in concentration, change in time. So that's all about the rate expression that you must learn in this chapter, and that your also your what else I could say, your book talks about, your text talk about. Then what is the average versus instantaneous reaction rates that we are interested in? When we perform our experiment, actually the way of performing experiment is that you either go over a very long period of time, starting from 0 to time 15, let's say, you just do it all the way, or you break it into different intervals, equal intervals, like 0 to 2, and then 6, then 8 minutes, then 10 minutes, and then some minutes here go all the way to 15. So that is the difference. Okay, you can do it for any particular time, or you can do it all together. So if you understand this part, that you can do it all together, or you can just, which is like a crude way of saying things, just bring it to the terminology of chemistry, is average rate reaction versus instantaneous. So average means the rate at which a reaction proceeds over a time period. So you can decide it at your own. And for instantaneous is the rate at which a reaction is proceeding at a specific time or concentration. Okay, so for the average, you're going to be calculating, it's going to be calculated using the concentration at the beginning and end of a time period. That's all it is. You're not going to be looking at, and you can take any time in between. Let's say if it is, you're calling it to be like different sections here, you can take it for any time slot here, or this slot, or this slot here. Whereas instantaneous calculated using a graph, concentration versus time that you're going to plot, and a slope of the straight line tangent to the curve at specific time, or by determining the average rate of reaction over a very short time period. That's what I said. If you are doing this very short time period here, That's instantaneous, which you're gonna call it determining by the average rate of reaction over a bit. So you are actually doing the average at this point by getting the by getting the curve, or by doing the average of the time slot in your uh, full plot that you say. Okay, so initial reaction rate, the instantaneous reaction rate at time zero, is what we call the initial reaction rate, because we assume that it's zero, but it's actually not exactly zero. So this is what I'm saying. If you are looking at the concentration of the reactants, then it is going down for sure, right? It's depleted. This is the rate of reaction versus the rate of reaction for the products, that you expect something like this, because initially the products are zero, so the rate of formation of product is also zero, and then it starts appearing as it goes up, and the reactants goes down. So we are looking at the chemists usually look at the reactants, because you know your reactants you're starting with, you do not really know what the products are going to be, and you actually know the concentration of the reactant that you're putting into the chemical reaction. So it's good control on the reactant means you're going to go with the reactant. So if you calculate the change in the concentration from from one time period, like say this is your initial time, this is your final time, then you have initial concentration, and then you have final concentration here. So you're going to take the difference. Let's say you're going to take because the concentration is on the top, so you're going to say the concentration final minus concentration initial over the time final minus the time initial, and that's going to give you the rate of reaction from one slot on this plot here. That's the change in time. You can get the change in time. You can get the change in concentration. And you should be able to calculate. So the concentration is going to be in molarity, time is going to be in seconds. So that's going to be, it means now you understand what is the unit of rate of reaction is going to be, meters per second. So relative rates of reaction means the rate of reaction may be expressed in terms of the change in concentration of any reactant or product. You can use the stoichiometry factor derived from balanced chemical equation. So for rate expressions, you can do all this stuff that I've already explained, that how you're supposed to do. Here we are just making the relationship between the reactant and one of the products, and between the products also. You know that in the stoichiometry, we can do all these type of relationships. So when we are talking about the speed of the reaction, what affects the speed of reaction, and that makes a lot more sense for you, that you know that when you need to cook something, you just give more temperature to it. You cannot just keep cooking by putting things on the stove and not giving extra temperature to it. Even for the tenderization of meat, you put it on the slow heat for a longer period of time, and then that's how you tender it, because the chemical reaction is happening there. So chemical nature of the reactants is one of the most important thing in determining the rate of reaction. If the reactants do not like to react, means there's something between them. That's because of their nature. When they are colliding with each other, these are not effective collisions, resulting in the chemical reaction. So sometimes in chemistry, we try to work on these reactions and see if we can have them work. But chemical nature is one of the most important things. And we know in the periodic table, if we go into the alkali metals, the top ones are not as reactive as we go down, okay? And it reacts at a faster rate in water compared to the second group, which is alkaline earth metals. So the state of subdivision of the reactant, what does that mean? The state of the subdivision of the reactant, the rate of most reactions increases surface area. How they are breaking up? If there are more surface areas, because the larger the surface area, more collisions are possible. Collision means the reactants must collide with each other for the reaction to. And first of all, keep that in your mind that the reaction is nothing. It's just a rearrangement of the atoms that you're giving into the chemical reaction. There's nothing new coming in. There's nothing going out of that chemical reaction. So it's just a new rearrangement. Rearrangement is always new, but this is a rearrangement that you are doing in a chemical, in a vessel. So the state of subdivision of the reactant also matter. Temperature of the reactant, for sure, temperature is one of the key things that affect the It's ordinarily increases with temperature. The reaction goes up, and you go and you put the and you reduce the temperature. The reaction rate becomes really slow. We put things into the freezer. We do not want to spoil it. We do not. Why we want to stop bacteria grow? Bacteria grow because the chemical reactions are happening. Their metabolism is our metabolism is also chemical reaction. Their metabolism is also chemical reaction. By reducing the temperature, we make sure that we stop their metabolism, and their metabolism is stopped. They're not using that food and not producing the excretions, and that's what we call the spoilage, right? So the temperature of the reactant is extremely important. Concentration of the reactants, make sure that the rate ordinarily increases with the concentration of the reaction. Is it true for all situations? We'll look at it. And situation is where which order of the reaction it is, and we have to look at the reaction orders. The catalyst, very important. It increases the reaction rate. So let's look at the dependence of rate on the concentration first. Then we'll look at the dependence of the rate on time, and then the third factor will be the temperature. So first of all, concentration. Okay, rate law is a new term that you see here, is different than the rate expression. Okay, it's going to be an equation that relates the rate of reaction to the concentration of the reactant. That's why we use the rate laws, because we are looking into the concentration factor of the reactant for the rate of reaction. It's raised to a certain power, and that's what we call the reaction order. Experiments must be done for rate law, not for rate expression. That's what I said, the different terminology. For the rate law, we have to do the experiments in the lab. We cannot calculate it for the with the balanced chemical equation. So for that, we have to go through what's happening to my computer today? Well, so let's say if you have just one reactant A in the chemical reaction, if you want to write down the rate law for it, the rate law is going to be equal to, we're going to write down rate is equals to the rate constant, the concentration of the reactant raised to the power this. This is what it says, raised to the certain power. This power is called reaction order. Okay, and we work for the reaction. We work to find out the reaction order in terms of the concentration of a reactant. What does that mean? M is the reaction of the order of the reaction. It is determined experimentally, not from the balanced chemical equation. Keep that in your mind. Again, emphasizing that rate expression is different than calculating the rate law or working on the rate law. So reaction orders are usually positive integers. So rarely they are the fractions. You're not going to come across the fractions in this course. Most reactions involve more than one reactant. You know that it's not as simple, right? It's just like having one reactant is most of the time it's going to be the decomposition reaction. It's not all reactions are decomposition reaction. So most reaction involves more than one reactant, and most common is two reactants. So when so how do I write down the rate law for the two reactants? It's nothing. You just keep adding your reactants and keep giving it a different superscript to show the order of the reaction in terms of A and the order of the reaction in terms of your reactant B. So the overall reactant order of the reaction is going to be the order of reactant A plus the order of the reactant B. So rate constant that we are talking about is the proportionality constant in the relationship between concentration and rate. So our task here is to, when it says that you have to have experiments done for this thing, then the data will be available to us. Once the experiment is done, data will be available to us, and we should be able to calculate the rate law and the rate constant. That's our task here. So when you're talking about the rate law for this reaction, like say, if this reaction we are following, we're going to be, and you know what we are doing, we are just talking in terms of the reactants. So we are showing the concentration of the, and because it's just one mole ratio, so you do not see any superscript here. So only reactants appear in rate law. K is the rate constant for the reaction. Okay, so understand order with respect to a reactant is the superscript that I'm talking about, and the overall order I've already told you is going to be the added of two order each from each of the reactants in the chemical reaction. Determining the rate law using the initial rate method is what you will primarily do in this course, in this chapter. Okay, and that's what we do when we design our experiment for A reactant and for B reactant. We actually do three experiments, which is always more than one experiment. Then you have the reactants in your chemical reaction. What we do first, we keep the concentration of A constant and we change the concentration of B. Sorry. In the first trial, what we do is that we go with one concentration. Let's say I am going to use a number for that. And I can say I'm starting with 1 and 1 of B. In the second experiment, I'm going to change A, but I'm going to keep the B constant. And in the third experiment, I'm going to change the B, but I'm going to keep the A constant. So that's how I'm going to see how the change in concentration of one reactant is going to affect, because I'm interested in the order of the chemical reaction in terms of the concentration of each reactant. And for that, I have to go with three experiments and I see what and I have to see what I'm doing here. Okay, and it means that's how it is. So, and when we'll do a practice problem, we'll see what I'm trying to say here. So here it is. Rate constants, the common reaction orders are these, where we are talking about the zero order, first order, second order, or third order, which we are not actually going to talk about, not going to work on. We are talking about it, but not going to work on the work problems related to the third order because it's extremely difficult to work on this, and it's not the scope of this course here. So units of K is the most important thing that students are not able to get out of their calculations. So if you're not able to get this unit correctly out based on what order the reaction is following, please just memorize this. So if the question is talking about, let's say it's a first order reaction, calculate the K. At the end, the correct unit is going to be per second. So you know that this is, even if you're plugging of the number is not going to, probably making some mistakes somewhere that is not going to end on per second, then you will lose points. So if in order to if you do not want to lose points, just know that you are calculating the rate constant for reaction order, which is first order kinetics. Then you have to report your K value to per second unit. Most important thing is that the units in the table can also be expressed in molarity instead of mole per liter. So instead of this, you can say molar concentration per second. Okay, you really do not need to. And this means per molar. Oops, sorry. And inverse, when we make -1 as a separate subscript, means we are trying to show it like it's in the denominator. Inverse. Okay, so this is a sign of per second or per molar per second. This is what we call. So you can bring it into the M, not necessarily M over L, because sometimes it is confusing and it's a lot of it makes your work a little messy when you just keep bringing M mol per liter, mol per liter. So this is what I was saying, that you have one reactant, you need to do just 2 experiments. Okay, and you have to change the concentration of your reactant and you see how the initial rate is gonna show up. And how do you get these numbers? You do the experiment and you calculate the initial rate by changing the concentration. So you get the data out experimentally. Now, how do you calculate the rate? That's the game here, that calculating the rate is the most important part. So you're going to be writing down, first of all, you're going to write down the rate law. So the rate law here is going to be rate is equals to K and the concentration of CH3N and the CH3 raised to the power M. This is what we need to start out, right? When we start doing, start working on it, then we have to find out that this is our a rate law, and for that we have to work with M. Okay, what is the way of working with the M? Is that you're going to divide the experiment 2, and I'm going to write it here, experiment 2 divided by experiment 1 That means that I have to divide both the rates and the concentration side by side. So I'm going to say initial rate of the experiment 2 divided by initial rate of the experiment 1 equals to the concentration of the second one is 2.26 times 10 to the power minus 2 and over 1.13 times 10 to the power minus 2. You're going to take it all the way to raised to the power m, because we're interested in the concentration, right? So what is the rate 2 and rate 1? Rate 2 and rate 1 is actually here. This is rate 2, so there's going to be 5.6 times 10 to the power minus 6. And down here is going to be 2.8 times 10 to the power minus 6. So we need to sort it out. We need to solve it for m, which is the reaction order. And if we go solve it step by step, we end up on 2 equal 2. So this is going to be 2 equal 2 to the power m. Okay. So in order to solve it for m, because we are working on it, we have to take the natural log on or log to the base 10, whatever you want to. But what I do, I'm going to take the natural log. So I'm going to say ln2 is going to be equal to n ln2. That's how I'm going to bring m ln2, sorry. M, L, and 2. That's what I want to bring the power down here. That's how we solve it, right? So then it's going to be M is equals to Ln 2 over Ln 2, which is equals to 1. So the reaction order is first order. Reaction kinetics is first order. So when it's first order, is now we're going to plug that into the equation, and we can calculate the rate. We can calculate the rate constants. For that, what we do here, that we rearrange the equation. And when we are calculating the rate constant, the standard is to use the data from the first experiment in your data table. And there you have initial rate and you have the concentration. So when I have rate is equals to k to the power a to the power m, I'm going to rearrange it. It's going to be the rate over the concentration of a to the power m is going to give me the k. Okay, so now I have this first experiment to go with as a standard. I'm going to use the information from here. What is the initial rate? Because I have already figured this out. I have figured out the reaction order is just 1. So it means I'm going to plug these numbers in here. And the concentration is 1.13 times 10 to the power minus 2 molar. And it's just 1. So it remains like this because the power of the value of m is 1. So that's going to go up here is going to come the rate, which is 2.8 times 10 to the power minus 6 here. Okay, so when we do solve, so on top it's meter per second, in the base it's molar per second, sorry. So molar cancels molar, and you know that the K is going to be in per second, which aligns with what we have learned here. Is the first order going to be per second. So the answer is, what is the answer when we divide it by this? Let me divide it. It's going to be 2.5 times 10 to the power. Here you have two reactants, but it should not bother you because you now know the way of doing it. It remains the same. So first you have to write down the rate law, which is rate is going to be equal to rate constant concentration of first one, which is NO raised to the power M, right? And then H2 raised to the power N. We can call them M and N. So these are the reaction orders that we are trying to calculate. And proceeding further on that is going to give us some understanding of how. So now we have to pay attention to what is changing and what is not. Experiment 1, experiment 2, experiment 3. So we started with these two concentrations first. Then we didn't change theirs, but we did change the concentration of NO. Then we kept the concentration of this constant, right? Like this. If you compare this to this, and then this is the difference here in the concentration of the second reactant. So we have to actually, the same way we have to do it twice. And I have to, for a second, I have to stop here and I have